Design and development of a smart transformer sizing tool. Our team members include Yusuf Afifi, myself Louis Leontis, Chantel Lee, and Kyle Zhang. The problem identification for this project is the net zero emissions goal by 2050. 8 actions are set to achieve this goal, one of them being zero emission vehicles. This will cause an increase in demand for electricity, which will inherently cause an overload of transformers due to the increased excess of load. The current solution for this tool is to calculate peak residential load based on the number of lots, type of heating, and average square footage. Once this is done, a diversity factor is applied to simulate a realistic peak load. The proposed solution for our tool is to include a low voltage scenario and to calculate peak residential load with the addition of EV loads, which will include the number of EVs, manufacturer, and level. Once this is calculated, a diversity factor will be applied and an overload factor will be applied to the transformer for optimal sizing. The design model for this tool will include 5 different levels. Level 1 being the input stage, which includes the graphical user interface and user inputs. Level 2 being the data analysis stage, which uses the previous inputs to determine the correct peak load, knowledge bases, and low voltage consideration calculations. Level 3 being the calculation stage, which is used to calculate the peak load of each transformer. And Level 4 being the transformer knowledge base stage to determine the optimal sizing and cost of transformers based on the output of Level 3. And finally, Level 5 being the output stage, which displays the peak load per transformer, number of transformers, optimal transformer size, and cost. This is the final product of our Smart Transformer Sizing Tool graphical user interface. To the left, we notice we have a customizable input lot section where we can add and delete rows for customizable use, as well as add the number of lots and square footage. We can also select between gas or electric heating using a drop-down menu, as well as choose transformer information, which includes the overhead or underground selection, and the primary voltage depending on the location of the development. To the right, we also have EV charger information, which we will come back to. And in the top left, we have currency conversion inputs. In the output, we notice that peak load is displayed, as well as optimal transformer size, the number of transformers, and the estimated cost of each transformer, as well as the total cost for the development. Now we will add EV chargers to display the difference in sizing between no EVs and EV simulation. As we can see in the output, our peak load for both summer and winter has increased by 20 kilowatts with the addition of these chargers. The optimal transformer size has doubled in size from 25 kVA to 50 kVA, and we have also increased the number of transformers by 1, which will inherently affect the cost of the development. The conclusion of this project was that our group was able to improve current practices used to size transformers with the inclusion of EV penetration. A low voltage scenario was also included to determine the number of transformers required to service a development. Also, a diversity factor was utilized to resemble a realistic peak load of a transformer, and an overload factor was applied to ensure an optimal size was being outputted for development. Overall, this tool is able to provide an optimal size and cost of transformers to benefit customer and end user needs. A special thanks to Dr. Waleed Morsi Ibrahim, our faculty advisor, and Dr. Qusay Mahmoud, our Capstone coordinator, for providing us the necessary guidance through the process of designing and developing this tool.